let us consider a very simple problem, or at least what appears to be very simple. Let's take a patch of the sky as seen through a telescope. Let's identify two stars in the sky. Now what I want to know is, I do know that the star on the right is brighter than the star on the left, but I want to know by how much. How simple do you think that problem is? Well, let's find out. So first thing we should understand is, how do we measure light? So we measure light using something known as photoelectric effect. So what happens in a photoelectric effect is that we receive some light and it gets converted to a charge, which I am denoting as Q. We can then measure the charge, and that is how we measure how much light we have received. Now we can solve our problem of determining which star is brighter and how much by taking the light from each star and measuring how much charge it generates. So let's say that the star on the left generates a charge Q and the star on the right generates a charge 5Q. So can I now simply say that the star on the right is 5 times brighter? Well, it's not that easy. Let's try and understand why. So the first thing that you must understand is that the photometer which I have and the photometer which you have can be different. So even though both our photometers are receiving the same amount of light, your photometer will generate a charge Q1 and my photometer will generate a charge Q2. And this Q1 need not be equal to Q2. Which means that world over, if I want astronomers to agree, we need to standardize our instruments. And that is not a straightforward process. The second thing is that you are using a telescope and I am using a telescope, and our telescope is a system of lenses and mirrors. And whenever light passes through a lens, it does not come out unscathed. Some amount of light is lost. So for example, in this diagram, there is a certain amount of light falling on the first lens, but when it comes out, there is a lesser amount of light. And when it comes out of the second lens, there is an even lesser amount of light. So, and the amount of light that is eaten away by the lenses or mirrors of my telescope and your telescope can be different. So we need to correct or standardize for that as well. Now, the next important thing, the atmosphere. Now, even though the Earth is a sphere, at any given local point, I can assume that the atmosphere is like a flat sheet as shown in this diagram. Now let's consider a star which is vertically above us. Its rays travel through towards the Earth and then pass through the atmosphere and reach the observer. Now let's consider a star which is at a higher angle compared to us. Its light also passes through space, enters the atmosphere, but you see that the amount of atmosphere through which it travels is more than the amount of atmosphere through which the other star's light travels. Now you might ask, how does that matter? Well, the atmosphere has an effect on the light. And one of the most dominant effects is something known as Rayleigh scattering. So what Rayleigh scattering does is that the atoms or molecules that are present in the atmosphere, they scatter away the light that passes through them. And they preferentially like to scatter blue light more than they like to scatter red light. And that explains why the Earth's sky is blue in color, because it's blue light which gets scattered more. It also explains to us why at sunrise or sunset or moonrise or moonset, these two objects appear very reddish. That is because most of their blue light is scattered away, and what reaches us is a dominantly red light, and that is why we see them in that color. Now, astronomers have to correct for this eating away of light by the atmosphere, and this eating away of light depends on two things. One, of course, is the position of the star in the sky. The other is the quality of atmosphere at any given time and at any given place. For example, in the winter, the skies of Pune are actually highly visible, but in monsoon it is overcast and we cannot see anything. In the same season, at any given time, you will find that the skies of Pune are always worse than the skies in Himalayas or the Hawaiian Islands, which, by the way, is why we like building telescopes in locations such as the Himalayas or the Hawaiian Islands. So we need to correct for this. Now, once we have corrected for the atmosphere, you might be thinking, okay, it's all done. Well, hold on. There is one other important correction that astronomers have to do, which by far is one of the most painful corrections that astronomers have had to deal with. So here is a map of the Milky Way, the galaxy in which our star system, the Earth and the Sun, is found. So you can see that the location of the Sun is marked in this diagram. Now imagine that we wanted to measure the brightness of a star, let's say indicated by that smiley. Now what you have to appreciate is that there is a vast distance that the light from that star has to travel in order to reach us. And in our own Milky Way, there is what we call interstellar dust, which has a similar effect to that of the Earth's atmosphere. It is eating away some of the light, and so we need to correct for that as well. And over the last several decades, astronomers have done intense studies at different wavelengths and constructed a map of how the dust is distributed in our galaxy. And it is using these maps that we are able to estimate how much of light was extincted or was lost because of the effects of interstellar dust between the star and the Earth. So let's make a list of all the corrections that we have understood so far. There is the instrument or the detector. We need to correct for its effects. Then there is the atmosphere, and the atmosphere in turn means that we need to consider the position in the sky. We need to consider which location on Earth we are standing and the specific day or time on which we are conducting the measurements. And we need to take into account the effects of the Milky Way. Now, depending upon what exactly you're studying and what wavelength you're studying, there are many other effects that also need to be corrected for, but these are the most essential corrections that astronomers have to do. So I hope you have gained some appreciation about how difficult it is to conclusively measure the brightness of an object in astronomy. Thank you.